Starting a minute late. I'll be sure to go a minute over to make it up for you guys. That's only fair. That's right. Yes. So I'll begin with some scripture. So my verse for today was Jeremiah 17:9, which says that the heart is desperately wicked above all things. Who can know it? It's a sobering but important verse to remember. I do think it casts a long shadow over the project of psychology. But anyway, I'll begin with a word of prayer. Dear Father, we thank you for this day. I thank you for this class. Just ask you to just guide our work today. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen. So, lest I forget, I'm supposed to take attendance in this here class. So, this looks like an attendance sheet. Yeah, we'll go with this one. Let me add a date. So while I'm adding a date to this sheet here, do you guys have any particular questions?
I did have a question about notation.
A question about notation. I'm intrigued. Well, we'll come back to it. So, if you find it, you can ask me later. You can find it or no?
I haven't quite found it.
You found? Oh, you found it?
I have no. Sorry.
Okay. So, example one. I want to talk about kind of a problem that involves, I suppose, two different things we've looked at, which is the inclined plane and the pulley. So here I'm gonna put pulley up. I'll put a pulley up here. I'm gonna put one mass over here. I'm gonna put another mass over there. I'm gonna connect these guys with a massless, unstretchable rope to make our life easier. And then to make things a little bit easier, to start with, we'll assume in motion, to the right. All right, so we're in the kinetic case. All right, and I forgot to say, if you're in this class, I need you to have the laptop shut while the class is going on, unless you're taking notes actively. So if you're not taking notes actively, the laptop should be shut. I tried. Anyway, I will make an announcement. Let's see here. So I'll make the announcement again. So I asked the laptops to be shut during class. Like, if you need to work on something else, just don't come to class. Like, it's fine. Like, you can just work elsewhere. Just don't work here. So I know, like, I take videos, so you can watch the class later. It's fine, you know. There's no need to come here to work. So here we have two masses, mass 1 and mass 2. And we've got friction. All right, so I'm assuming a coefficient of friction of like mu. All right, so it's in motion. So we've got a force of friction involved. And the question then is, what's the acceleration if you have, and I guess I need to also define this angle here as alpha, and this angle here is beta. All right, and I'm not assuming that the top is a right angle or anything like that. Okay, so this is just an inclined plane, possibly unequal angles. The question is what happens. So we're going to assume it's in motion to the right. So how should we solve this problem? Like, what goes on? What do we need to do? Free body diagram, right? So what are the forces at play? You've got tension this way. You've got tension that way. All right. Since the rope is massless and unstretchable, that has to be the same tension. All right. So I'm not wrong to use the same letter T, but of course it pulls up on M1 and it also pulls up on M2, I suppose. But anyway, the rope is not going to push M2 down the down the plane, right? It's going to pull up. All right, then what else? We've also got normal force 1. And over here, we've got normal force 2. We don't know what those are a priori before the fact. And what else? Well, gravity. We've got two pieces, right? On the one hand, you've got this part of gravity, which is M1, M1G, what you got? Cosine alpha. And then this guy, I'm gonna draw it longer just to make it so my picture's easier. This character right here would be M2G cos beta. Right? What else is going on? You've also got the part of gravity which goes this way, right? Let me draw it. This is not the scale. I'm just making it so I can make my labels easier. This one is M1G sine alpha. And of course, this character over here, drawing it ridiculously long for the sake of separating my labels, M2G sine beta. Actually, keep in mind these pictures, does the length of the vector really mean much? It doesn't. I don't mean anything particularly by the length of the vector. They're just meant to, you know, illustrate all the forces. Yep.
We're now looking at a vector that's pointing like r vertically down in regards to M1G or M2G.
Right. As I said, I'm not really doing this correctly because the sum of these two should be vertically downwards. Like that, I'm admitting I'm not minding that. You're absolutely right. The picture should be like M1G, technically speaking, should be like this, right? And there's like a piece that's like that. And then there's another piece that's like that. So this one would be M1G sine alpha. And this is the M2G, M1 rather, M1G cosine alpha. And alpha's here, I suppose, in that picture. Admittedly, my lengths of the vectors is not, yeah. So I'm just using the free body diagram as a guiding principle for setting up Newton's laws, yeah? I've got almost everything. I said there's friction involved, so what am I missing? Well, friction, right? So there's two forces of friction here. What direction do they go? Well, I told you the motion's to the right, right? So we're talking about kinetic friction, so it's the, you know, does friction go in the direction of the motion? No, right? Opposite. So that means that the force of friction 1 is like here, whereas the force of friction here is like that. Force of friction 2. Force of friction 2, there's 2. All right, so we have everything we need. Let's write down Newton's laws. So Newton's laws. Let's start out with the boring ones, the perpendicular ones. Perpendicular for M1, perpendicular for M2. What do those give me? So perpendicular for M1, I've got 0 is equal to Fn1 minus M1G cos alpha. For the M2, I've got 0 is equal to Fn2 minus M2G cos beta. That's it for the perpendicular sense, right? And the acceleration has to be 0 because it's staying on the plane, right? Now, it's important to get in the habit of writing down Newton's laws and thinking through Newton's laws in the case that something else happens. Like, you can't just look at my example and try to extract a formula and just use that for other things. Because if in the other problem you're looking at, like there was some dude pushing on one of these boxes, like with an additional force, that would mess up the normal forces. You know? So it's important to think through this process in each problem we do. But this isn't the first time we've seen this. The normal force in this case is M1G cosine alpha for N1, and the normal force for N2, for mass 2, is M2G cos beta. Great. And so, hence, the force of friction, 1, which is equal to mu sub k times the normal force on 1, is just mu k M1 G cosine alpha. And likewise, the force of friction on 2 is mu k Fn2 by basically definition of friction, mu k m2 G cos beta, I believe. Yeah. So then what? All right. So then let's turn to Newton's laws in the parallel sense, right? So like m2, rather m1 in the parallel sense, we've got m1 a is equal to what? So let's see here. We've got looking at m1, yeah, t. So that t is pointing in the direction. So you're whoever said t, you have just defined the positive sense for us. Good choice. So you're saying to the right is positive. All right. Yeah. But just because the motion's going that way, you don't have to make it positive. You know, you're free to choose otherwise. But anyway, t, so then I've got minus F1, force of friction 1, and minus m1g sine alpha. There you go. So that's Newton's law on m1, looking at the parallel component of the force to the plane. If we look at the parallel component for m2, what we got? We've got m2a. By the way, the reason that they share the same acceleration is that there's a stretchless rope attaching them, right? Which means the motion of one is coupled to the other one precisely exactly the same. So they share the same acceleration. Of course, we've now defined down the plane as positive, right? Keeping with that pulley. So m2a is equal to minus t, right? Minus force of friction 2 plus m2g sine beta. And there you go, that's Newton's laws. All right, so this is the order of operations for solving these problems. Understand the problem you're looking at, identify all the forces involved, draw free body diagrams, do trigonometry to separate the forces into two convenient perpendicular directions, then look at the equations in each one of those directions, in this case parallel and perpendicular, and then write down Newton's laws, see if you can solve for whatever you're interested in. At the moment, I'm interested in the formula for acceleration. So the formula for acceleration here, I don't really care about tension, let's say. So I'm going to do the same thing we did last class. Sorry to, it's like a broken record, but we're going to do what? We just do what? We add the equations again, right? Adding the equations will cancel the tension, and it's going to give me, you know, m1 plus m2, factor out my a, is equal to, well, what we got here? M2 g sine beta minus m1 g sine alpha minus minus the force of friction 1 minus the force of friction 2. And then, of course, I can, you know, if you don't mind, guys, I'm going to erase this picture over here. I hate this thing. I hate it so much. I forgot to bring my eraser shirt this morning to calculus, and I ended up erasing with this thing, and it was the most unpleasant thing I've done today. Ugh. What's that? Oh, pull a Sprano? Well, but I've got the shirt, so I don't. But you make a good point. I could just Sprano the board. It's a verb. It works. All right, so just don't call him soprano. I hear so many students call him Professor Soprano. It's like he's not in the mob. Let's see here. So we've got lo and behold, we've got m2 g sine beta minus m1 g sine alpha. If you want to put, we have formulas for the force of friction, right? So if I'd been smarter, I could have done some algebra here. Let me try to be smarter. Give a second here. Look at it. There's M2, like if you see these equations here and here, see those? If we plug those into here, we can just factor out M2. Keep all the M2 stuff together. There's like an M2 G sine beta minus what? Force of friction 2 gives me a mu k G cos beta.
You can factor out a G2.
Oh, you could factor out a G2? All right, fine. You talked me into it. I'll factor the G out. M2 G. See, look, I did it. You guys happy? All right, sine beta. What was I? I had to make another mistake. Don't worry, it'll come. Mu k cos alpha, and then plus m1 g times. Let's see what we got. Well, let me make that a minus. See, there you go. Not a full Sperano, just a partial Sperano, just one finger. Still counts. So minus g sine alpha, and then plus mu k cos beta, I guess. That feels wrong. I think that's supposed to be a cosine beta there, wasn't it? Yeah, this was a, hey look, I told you. Let's see here. Mu k cos alpha was supposed to be here. All divided by m1 plus m2. And there you go. That would be the acceleration in this situation. Any questions? I mean, we can put in numbers and see what happens and stuff, but really the issue is more the setup. Yeah.
When we're writing out the sums of the forces, how would you like us to?
Use words.
What would you like?
Just use words. Like, this is Newton's second law for M1. Like a sentence.
Okay.
Something like that is. Or you could use my shorthands, like perpendicular for M1, perpendicular for M2, M1 parallel, M2 parallel. Maybe just like write the words Newton's laws above, so I know what you're doing. I do mostly grade the answer in here, that is true. So if you do horrible things, but you come to the right answer, I don't usually take off points, unless I just see something that's so abhorrent that I'm like, physics demands that I do something about that. It's just too wrong. I can't not look the other, you know. But anyway, your goal in writing the solution should be to convince the professor that you know what you're doing, right? Generally speaking, that's your goal. Trick us into thinking that you know what you're doing. You know, if you can do that, then you've achieved something. So, so here's the mistake I made last year. Last year I tried to work this problem, but I didn't make it in motion. I just asked, it's at rest, does it slide? So how would this analysis change if we didn't know if it was in motion?
Wouldn't we need to know what the masses were before we could determine whether or not it was going to slide?
Possibly, but even that doesn't help.
We wouldn't know the friction.
What's that?
Coefficient of friction.
Let me just take a second here and work it out. Let me work it through you. Let me show you the issue. Yes, sure, maybe we should know them. You're right. If we knew the masses. What I'm about to show you, with just a little bit, really not much more calculation than we've already done here, is that even if you knew the masses specifically, and you knew the coefficient of friction specifically, and you knew the angle specifically, if it starts at rest, there's not, like if I gave you all that, and then I asked what's the tension, you couldn't tell me. There's not a unique answer. And the reason for that is as follows. So let's just walk through it a little bit. If it's at rest, then we have A equals to 0. Okay? And the analysis is unchanged. Pretty much, right? Same free body diagrams. Yeah? Although, technically speaking, in the case it's at rest, we logically should allow the friction forces to go either way because we don't know the direction of the potential motion. But I'm just going to leave them as they are in the equations with the understanding that they could be positive or negative. And so if you do all that, well, you just get 0 is equal to T minus force of friction, right? Well, let me just get to the point. Through the same algebra we just did, you just get to that, right? So what you would find, just going straight from here, we would find that the force of friction 1 plus the force of friction 2 is equal to m2 g sine beta minus m1 g sine alpha. That's the equation we would get for the sum of the forces of friction. But in the static case, where what we'd have, see, we don't have that. What we have is that the force of friction 1, we would have minus m1 g cos alpha less than or equal to force of friction 1 less than or equal to m1 g cos alpha. See, those are the theoretical maximums of the force of friction going right or left. That's the most friction you can get in this situation. Likewise, if you had this one, m2g cos beta less than or equal to force of friction 2 less than or equal to like m2 g cos beta. Yeah, same thing. All right. I forgot I'm missing something. What am I missing? Kind of an important thing. These are friction, right? The coefficient of friction, right? Yeah, maybe that. So throw in a mu sub s here for static. So, like, if I granted you, this is the mass 1, this is the mass 2, these are the angles specifically, I gave you all of that. Like, just hypothetically, hypothetically you could suppose that this, maybe this is 20 newtons, maybe this is 10 newtons, right? If you did that, that will force a particular thing up here, which I don't really want to spend class time. If I tell you this and that, then that forces a value up here. You have enough information to figure out what the mass and the angle is if you have this information, if you know the coefficient of friction. So that would make this some number. Let's just call it C, just for the sake of discussion. I don't really want to do numerics here. It would eat 20 minutes of class. We would learn almost nothing from it. But if we did that, you can draw a graph. Force of friction 2, force of friction 1. And what you're looking at then, if hypothetically you were given masses and coefficient of friction and angle such that that works out to 10 newtons and that works out to 20 newtons. So you're between minus 10 and plus 10 here. All right, for force of friction 1, and you're between 20 and minus 20 the other way. For F2. And then that equation at the top is F1 plus F2 equals to C. Well, that's nothing more if you look at it in terms of this graph, which is helpful to understand what we're dealing with. The equation is that the force of friction 2 is equal to that constant, whatever it is, minus the force of friction 1. Which would, and that constant will be less than 20 and 10. So it's like in here somewhere. When I worked it out, it was like 11 for the angle I chose and the friction, coefficient friction I chose and stuff. I have a picture on my phone if you want to see it after class. And the line is like this, right? Because it's slope with -1, something like that. So physically speaking, anything from here to here, this does not actually intersect this is not equal to this is not actually going through the axis, okay guys? Like there's some whole infinity of possible choices for the force of friction 1 and force of friction 2, which will result in static equilibrium. So I was not expecting this when I walked into class and tried to work this problem out. And I made some simplifying assumption which was actually like not true. And then I afterwards I had doubt about it. So I went and asked Professor Dromby to work it. She worked it. She got one answer. Then I took it home and asked my wife to work it. My wife has like she's taken like more than 30 hours of physics in graduate school. She's an elite physics student actually. And she got a different answer than Professor Dromby. Oh, this is troubling. So my wife is not dumb. And then I asked another professor, and he got the same answer as Professor Dromby. I'm like, and then I worked it again, I got a different answer. It's like, what's going on here? And then I brought it back to class and worked it a different way the next day. And then I decided I didn't like that, and then I brought it to class a third time and gave yet another correction to it. But this is ultimately the answer to this problem, is that it doesn't have a unique answer unless I give you some kind of additional data about how it's resting on this inclined plane. So I actually got a formal complaint in this class over this example. Someone complained over this actually, that I didn't know what I was doing. And it's true, sometimes I don't. But I do like to at times go into class and try a new example. And you guys should know that if you try a new example in physics, you may or may not be able to do it. So what do? Try again. I tried a third time. You shouldn't do this in class as a professor apparently, because I got a complaint. Although that same student also complained that I gave too much extra credit in here. And every student I've ever told this is confused and bewildered by this complaint. But nevertheless, the complaint was made. So I'm giving less extra credit this year. So, yeah. Did I hear a bro? You count me as a bro? I'm honored. I don't even lift. See here, except for children. So, anyway, this phenomena of there not being a single answer should not be surprising to us, because we've already had an example like this. If you just put a box on a flat plane and then ask what forces will not move it, it's not a unique answer. It's every horizontal pushing force up to the static limit of friction, right? Zero force doesn't push it. Half the maximum force of static friction doesn't move it. 3/4 of the maximum force of static friction doesn't move it. Only when you just get past that, static maximum of friction does it move. That's not one answer. There's an infinite choice of answers between 0 all the way up to the static friction. This is just like that. It's on a tilt, so it's less understandable. Anyway, example 2. Let us suppose we have a box with mass m, and we give it a shove with velocity v0 up the plane like so. All right, and so it's got velocity v0, and I'll put it at the base of the plane just to keep geometry simple here. All right, and let us suppose that the plane has angle theta. All right, so obviously it's a kinetic problem. My question is simply, how far up the plane does it go? So how far up the plane? Does m go? And I guess to be more specific here, I really need to tell you what I mean by up. Your choice. Do you want me to mean do you want me that to mean the parallel direction, like actual distance along that's what you want? Okay. So parallel to plane. See, because if it gets up to here, right? If this is the final resting place, Vf equal to 0, right? Suppose that's where it gets to. Then that distance, you could call this distance h, right? The distance we're interested in by your choice, let's call it d. How are d and h related?
Pythagorean theorem.
Pythagorean theorem? Oh, that's true. But I was looking for like tangent. Tangent theta equals to what?
What did you sine theta say?
Oh. Oh, yeah. Oh, hey, another opportunity. Thank you. I'm now looking at every mistake as an opportunity to emulate Sperano, which I feel like is a good thing, because Sperano is well loved amongst you guys. Let's see here. Man, if Dr. Sperano taught physics, his tests would be impossible, right? Like his tests in Calc 2 are like, they're not easy, are they? Oh, okay. Oh, I'm sorry, too soon? I wasn't trying to strike the fear of Sperano into you, but oh well. I hope you can complete the square. Let's hear. All right, so how far up does it go? Like, why does it stop? I guess we need to, I'm going to assume that the force of friction is equal to mu, let's say, yeah, mu, what is it? Mu times the normal force, right? Okay, so what's going on here? You've got the normal force, you've got mg cos theta, you've got your mg sine theta this way. So what do we got? We've got mass times acceleration is minus mg sine theta. Now, which direction does the friction force go? Down, right? So force of friction's like this. So I should do minus mu. And what is in this case, the normal force is what? Mg cos theta. To be clear, the logic I'm using there is writing Newton's law in the perpendicular sense, and then it's equal to 0 because it's not accelerating into the plane, and so I can solve for Fn equals mg cos theta, right? It is not the case that Fn is always mg cos theta. I talked to somebody in my office. They accused me of saying that Fn is always mg cos theta. This is not true. I will not accept this accusation. It's usually that, though.
Sorry, sir. It's because
Yeah.
the only force pushing down is gravity, correct, sir?
Because the only force of pushing down is gravity is the correct answer. Yeah. So there you go. I think that's it for the parallel direction, and that's really what we're interested in. Divide by the mass. What we got? Acceleration is minus g times what? Sine theta plus mu cosine theta, I guess. If I factor the minus out and such, divide by m. Okay, so let's put some numbers in. You're like, could you put some numbers in ever? Yes. Let's do it. I'm not going to give you the mass because it's irrelevant, right? Mass doesn't matter. Let's see here. Let's choose theta equals to, let's say, 30 degrees. We'll choose a coefficient of kinetic friction of 0.3. And yeah, that should do it for us. So that if those are given, what we got? Minus 9.8 meters per second squared times the sine of 30 plus 0.3 times the cosine of 30. So what's that give us for our acceleration? Oh man, I've got no calculator.
Negative 7.4461.
I have one vote for negative 7.446 meters per second squared. Any next vote? Next answer. Oh, we got another. Oh, if there's two, it must be true, right? That's like a basic physical law. If there's two, it must be true. Yeah, two or more witnesses. Well, I mean, there were two large theory groups that said that the like the mass of the Higgs boson was like two different values, but they were kind of close, so it's right. I think that their answers were within the margin of errors of both groups to be, I don't want to poo-poo the work of hundreds of physicists, yeah.
May I ask, why in that force summation is both mg sine theta and mu mg cosine theta negative?
Because they're both acting against the motion. We said it's given a push up the plane with velocity v naught.
I see.
Okay, so that's the acceleration. What would you guys like your initial velocity to be? 100 meters per second. I like it. It's moving. That's substantial. Well, I don't know. That's about like an airsoft gun, isn't it? That's what, like 328.1 feet per second? It's kind of a weak airsoft gun, right? Like one of those spring-loaded ones. I still need to get an automatic one of those so I can like play with my children. I feel like if I've got the automatic one, then I don't need body armor, right? So now that I have this initial velocity, what should I do? Is this velocity constant? Search your hearts. It is true. This is a constant velocity. Is this acceleration constant? It's a constant acceleration. So we can do the timeless equation. We have Vf squared equals to V naught squared plus 2a, well, as we're calling it, d. So d apparently is equal to minus V naught squared divided by 2a, which in our case is minus 100 meters per second squared divided by 2 times minus 7.46. Notice the minuses, they be canceling. And the units work out too, right? Because you've got a meter squared over second squared divided by meters over second squared, which leaves us with a single meter. So what do we get? $671.5. There you go. So about a half a kilometer up the hill. Wow. Really?
That's impressive.
That feels wrong to me. I guess that is really fast. Yeah. So if I had 10 meters per second, how far would I go? If V naught equals 10 meters per second, how far would I go up?
6.715 meters.
Just that?
Because if you divide by 10, that's
Yeah, that would.
100 squared.
You're exactly. So you multiply by 10, you square it, so you divide by 100 to get that. Yeah. You are correct. So that feels right. Okay. So my question then is, okay, if this is the situation, does it slide back down? Or does it stay put? So follow-up question. Does it slide back down or stay put?
Do we know the coefficient of static friction?
That's the issue, right? What is the coefficient of static friction? That's what we need to know to answer this question. Let's see here. So we'd be up against the equation for static equilibrium. You have 0, is minus mg minus mg sine theta. And then I think we should put plus the force of friction in this situation, because when the force of friction will reverse its direction when it starts to try to slide back down, right? The force of friction is no longer going down the plane when it starts to slide back down, it's going up, right? So it would look like this. And then, so the question is, and of course the force of friction is mu sub s mg cos theta. So the question is, can we solve this equation, right? Is it possible to get the force of friction is equal to mg sine theta? We know that the force of friction is less than or equal to mu sub s. I've got my inequality backwards. It's less than or equal to mu sub s m. You guys couldn't see it though, I was in the way. G cos theta. So the m's cancel. And the question just becomes, is it the case that mu sub s times cosine theta is greater than or equal to sine theta? If that is true, it does not slide. If it's not true, if on the other hand it is the case that mu sub s times cosine theta is actually not as big as sine theta, it's going to slide back down, because the static force of friction is not enough to keep it from sliding back down. Does that make sense? So, yeah. All right, so we are going to move on now. So the next part of this course, it's about work and energy. Work and energy. So I need to talk to you guys about what is work and what is energy. Now, we're not going to talk about what energy is right off. We have to start by defining work. So I'm going to do it in some stages, because I know not all of you have had high school physics. So some of you may have never seen like the proper middle school definition of work, right? So let's talk about, how do you define work? What is work? Work is something that's done by a force. So, what is work? So I'm going to start by giving you some special situations. So here's the special case. If the force F is constant and in the direction of motion, in other words, it looks like this. So you've got some box, whatever, and you've got a force F naught like this, and the box goes from here over to here, a displacement delta x, all right? So we've got a constant force in the direction of motion the whole way. Then the work done is simply F naught times delta x. It's simply that. All right. So the units of work are like newtons times meter. A newton meter is the unit for work. So that's case number one. Case number two, suppose you've got a constant force, but not, same direction as displacement. So here we could have something like this. We have a mass m, all right? It goes over to here by some displacement delta r. So here's its, its final. Forget about the mass. Let me put a box. Take a box, move from here to here, whatever. A box, a car, some physical object you're having the force act on, all right? So if it goes from one point to another, again, the force is constant. So, but this time we got to think about it as a vector. All right? But it's the same at each point along the journey, all right? So constant force. It turns out in this situation, the work is simply equal to the force dot the displacement. So and that's the dot product. So in particular, what does this mean? If the force is perpendicular to the displacement, the work is 0. What happens if the force is in the same direction as the displacement? Well, this formula just simplifies back to what? Magnitude times the length of the displacement, right? So we're back to the original case. All right, so next case. What if you've got, we'll keep it one-dimensional. We'll let the force be, like this here. We'll let the force be like this here. But here we're going to have f of x1, and over here you'd have f of x2. All right. What I'm saying is you've got you're applying a force to a mass, and it's always in the same direction as the motion, but the force is variable. All right. So in this kind of situation, what you want to think about is the little tiny itty bitty amount of work done would be equal to the force at that position times dx. That would be the little bit of work done as you're displacing it over a little dx. See, even though the force is variable, it's constant if we look at an infinitesimal displacement. So in this situation, if we're going, say, from x1 over here to x2, the work done going from x1 to x2 would be defined to be the integral from x1 to x2 of f of x dx. So if the force is variable, we need an integration. All right? Now we have not yet defined work, though, because what are forces? Our forces, so let's think about this. As you think about forces that are applied to physical motions, are they constant? They might be. Are they always in the direction of motion? Maybe, maybe not, right? So the full story here, the proper general definition of work, has to address both of these issues. It has to allow for variable force, and also it has to take into account to the direction. And that is why we give the following definition. The work done by a variable force is defined to be the integral from time 1 to time 2. Well, let's say from point 1, from r1 to r2, is simply equal to f. I'm sorry, guys. Let me dial it back here a second. I need to introduce some notation. So the integral of f dot dr over a curve C is equal to the following. So the curve could go, say, from here over to here. It's got an initial point and a final point. So let's suppose that the initial point is r of t1, the final point is r of t2. The position along the curve is r of t, like we've talked about. So you guys have found some position vectors already, yeah? So the work done by a force along the curve is defined to be the integral from t1 to t2 of f of r of t dotted with dr dt times dt. In other words, to calculate the work done by a variable force over a path, you need to know the trajectory that was traveled. And then you take the force field, you evaluate at the path, and you take the dot product with the velocity, integrate that up, and that gives you the work done. So this is, if you look at this is what we're looking at here is force dot velocity. So that's the definition of work. And so to properly understand work here, we do need to take a little bit of a detour into Calculus 3. So like next time, I will be sharing with you some of the rudiments of Calculus 3 that we will need for this course. So if you're, already in Calculus 3, some of this will be a review, but there will be new things for everybody, so don't worry. I don't want to give you too much lecture for one day. I'm going to stop here.